So vectors are usually used to they're frequently used to describe motion. We're going to talk about using vectors to describe motion, some motion along a curve. So when we do this, vectors are actually, as far as calculus is concerned, they're usually pretty easy problems. So the only difference is that we have an x position and a y position, or the horizontal position and the vertical position are dependent upon t. So they're not, one isn't dependent on the other, they're both dependent upon time. Right? So really the thing that makes this a vector is we can write it as a vector, and you'll see the notation will change depending on the textbook or the author or whatever, but frequently we use these sort of triangular chevrons on either side, and so we put the expression for x first, and then the expression for y comes next. So we would call this the position vector. Alright, so it asks us to find the velocity vector when t is equal to 1. So really all we do is we take the derivative of the x position and the derivative of the y position, and then we plug in 1. So there's nothing really difficult about this. It's really a notation thing. So t cubed plus 4t squared, we get 3t squared plus 8t. And then we have 4t cubed minus 3t squared. So this is, this is v of t. We have not plugged that t value in yet. So this is our velocity vector. It's the derivative of the position vector. And then if we plug a 1 in, now I have v of 1. So the velocity vector when t is equal to 1 is 11, 1. So we have a velocity of 11 units per time, whatever the time unit is, in the horizontal direction, and 1 unit per unit of time in the vertical. It asks us to find the acceleration vector when t equals 2, so we take the derivative of the velocity vector. So we need a of t. This is just v prime of t. So we take the derivative again, we get 6t plus 8, and what's that, 12t squared minus 6t. And we want the value of the acceleration vector when t is equal to 2. So we want a of 2. So again, we just plug 2 into our now acceleration vector, and we get 20 and 36. Alright, so the next example, we have a particle moves on the xy plane, so that at any time t is greater than or equal to 0, the position of the particle is given by these x and y equations. So we're trying to find the magnitude of the velocity vector when t equals 1. Alright, so let's find the velocity vector first. So v of t is just the derivative of the x and the y position. So we have 2t plus 3, and then 3t squared minus 6t. And so if we find that when v is equal to 1, when time is equal to 1, t is equal to 1, we get 5, negative 3. All right. So think about this velocity vector just in terms of, we have a horizontal component of 5 and a vertical component of negative 3. So the resultant velocity vector is going to look something like this. And so all we really want to know is what's the length of that velocity vector. That's the magnitude of the velocity vector. Right, so it's really just an easy Pythagorean theorem kind of idea. For the magnitude of a vector, sometimes you'll see it written looks like absolute value symbols. Sometimes you'll see two lines like that, It really just depends on what symbols are available to the textbook editor, depending on what they use. So this is just 5 squared, square root of 5 squared plus negative 3 squared, which gives us 25 plus 9. So the square root of 34 is the magnitude of the velocity vector. Third example, describing a particle moving. Again, we have expressions for x and y. We're talking about a time between 0 and 2 pi. And so it tells us that the particle intersects the x-axis twice, and it wants us to write an expression that represents the distance traveled by the particle between the two x-intercepts. So we don't have to evaluate this, we just want to write an expression that represents it. So first we need to figure out when does this happen? When do we get an x-intercept? Well, we get an x-intercept when the y coordinate is equal to 0. So we can set 1 minus 2 sine t equal to 0. And that's going to be true when the sine of t is equal to a half. And we're going to look between 0 and 2 pi. So when the sine of t is equal to 1/2, we know that's the case when t is pi over 6 or t is 5 pi over 6. So we know that our distance traveled is going to be the integral from pi over 6 to 5 pi over 6 dx dt squared plus dy dt squared. So we need dx dt and dy dt. Those are pretty easy to do. We can find them up here. So dx dt is equal to 4 sine t, and dy dt is going to be equal to negative 2 cosine of t. So we'll put those in here. We have integrating from pi over 6 to 5 pi over 6. And we have our dx dt, which is 4 sine of t squared plus dy dt, negative 2 cosine of t squared. And that's my expression. So that's an expression that represents the distance traveled. It told us we didn't have to evaluate, so I'm going to stop right there.